Today we have the pleasure of interviewing Olivier Dauchot. Olivier is the director of the Gulliver Laboratory in Paris, which belongs to the National Center of Scientific Research in France. His main interest is to develop model experiments and theoretical frameworks to study features of many particle systems driven out of equilibrium. This had led him to study a very broad range of experimental platforms and phenomenology, such as the behavior of granular media, glass-forming systems, active matter, and programmable matter. Can you tell us a little bit what is active matter?
Yeah. So active matter is, matter means something like, the everyday matter. So it's composed of plenty of units like atoms in general. So active matter, instead of atoms, your little units are like little animals or little robots or little something that can take energy from a battery or from the food they ate, and they can use this energy to produce some work like walking or pushing on something. And you study active matter because you study when there are billions of them together and you're interested in the general properties of your material.
Why is it interesting to study active matter, and what can we learn from studying such systems?
So 21st century, if we look around, so we have understood the materials, but then there are all the living systems. And the living systems, they obey a bit different laws. And this is because you are what we call systems that are outside of equilibrium. We permanently move, consume energy, dissipate energy, etc. And so active matter is somehow the continuation of physics to understand better living systems. Active matter was born in 1995 when the physicists proposed to study the collective motion of birds in the sky by a simple physics model and not by understanding all the biological mechanisms that play in each bird.
What do you specifically use to study these active matter systems? What are your tools to work with?
Yeah. So that's a good question, because as I said, we are motivated by this biological system, but I'm not a biologist. So I try to mimic biological system with physical system. Mm-hmm. So for instance, if you are interested as a biologist as the motion of large herds of sheep, well, you will study sheep. In our case, what we will try to do is to have, for example, you can buy on the internet little toys that are called X-bugs. And these little toys, essentially, there is a little battery inside, a little engine, and then they can crawl like bugs. And so you can imagine that you buy 1,000 of them, and this will be your population of sheep. So then you don't have to deal with sheep, you don't have to feed them, you just have the batteries. But you hope that what you are interested in is how much they move collectively, etc. Actually, it doesn't depend very much whether they are sheep or the X-bugs that you bought on the internet. And so my tools are always little things that I either buy or design myself that will mimic the minimal properties of the biological system I'm interested in.
This is really interesting because you can simplify a really complex biological problem to a robot that you have designed in your lab or you have bought that has maybe 3 or 4 parameters that you can play with. Can you tell us a little bit which are these 3-4 parameters that you can play with?
Indeed, this is exactly the idea. So again, let's take again this example of the sheep. So the sheep has 4 legs and they eat grass and then they move at a certain speed. But my X-bugs, they have like 8 legs and they don't eat grass, they consume the battery and they move at a certain speed. So it seems what is important there is the speed. Then the sheep has a body. A sheep cannot cross a sheep. And it's important also that the X-bug has a body, and then maybe the shape of the body matters a little bit. So the sheep is a bit elongated, the X-bug also is a bit elongated, and so the shape could be a parameter, for instance. For instance, if you put all your sheep or little toys in an arena that has a circular shape, you're likely to observe more like vortex-like motion. If you put them in a lane, probably it will be more like a line motion in this. And also you can ask yourself what happens if I put some kind of disorder in this environment, like pillars in the middle of the motion. Will it destroy the collective motion or not? And or for instance, people have studied this time for real sheep When ships try to enter, the place where there is food, they always jam together, then they more or less climb on each other, it's a real mess. And eventually they can hurt themselves, and so that's bad.
This is something that it is done. Like they have found out that if you put a pillar in the middle of a door, you exit more easily, which is kind of like counterintuitively that if you have the door completely open.
Yes, indeed, because you generate more fluxes, and in the airports and some places you can find things like this. Yeah.
But you can have active matter also in like solid systems, isn't it?
Yes, so we started with studying fluids, so I was asking more and more myself, okay, but what happens now if instead of a fluid we have something that is more solid, which happens also in standard materials. If you take a fluid and you compress, at the end it behaves more like a solid. And so I was asking myself, these flows of active stuff, if we compress them and we try to prevent them from flowing, what do they do? And so then we started to study not active fluids, but active solids. When you try to make them solids, essentially the conclusion is they still always try to move. So when you compact them like mad, they form a solid, but the solid still flows, but they start oscillating, like if your table was jiggling alone, spontaneously. Your heart is beating also, and all these kind of oscillations that are absolutely omnipresent in the biological systems.
So if you had to describe your career in 3 words, like which 3 words would you choose? And why?
In 3 words, well, I would say it's enthusiasm and a lot of fun and the pleasure of the discovery, all this. The second thing would be it's not easy in the sense that it's something where, you are your own boss in research, which is great, you are extremely free, but it means you are also your own evaluator. And looking at yourself every morning in the mirror is not always the easiest thing in life. So you have to ask yourself, are you making the good choice all the time? And you don't have much people to get advice from. So this kind of solitary evaluation is something that makes this job a bit tough. And then the third word is, yes, I would say is all the collaborative sides of it. Is you never do progress alone on your side. At minimal anyhow, you read papers from others. It's really a collective movement that drives the research to make progress, and which I really like. Okay, and to finish, what would you recommend to a young scientist? Someone who's studying physics. Well, first I would tell him to do the kind of research he wants to do, that is try to go towards his own questioning. There are trends, there are effects of fashion, there are topics that are more fashionable than others. He will always have time later to adapt a little bit. It's not good to work alone on your side, but you should really be motivated by your questions, because otherwise you are just doing somehow applied science to questions that belongs to others, and that's not enough strong motivation to face what is tough in this job, that you fail, then there is success, so it's extremely non-monotonic feelings. You can go, feeling very bad because nothing works during 3 months, then you're extremely enthusiastic during 2 weeks, then again it crashed, then it jumps again. So psychologically you need to be a bit strong, and this strength, I think you find it in the fact that you search to get answer to your own questions. So I think that would be my strongest advice. Okay, so this is the end. So thank you a lot, Olivier, for responding our... Thank you for your question.